Dear students, I am Dr. Nuzhat Gul from Department of Chemistry, Government College for Women, Ami Road, Srinagar. Today, I'll be discussing with you electromagnetic radiations, their features, and I will also discuss a little bit of electromagnetic spectrum. So, let us first start with electromagnetic radiations. What are basically electromagnetic radiations? Or we may say, how are these electromagnetic radiations generated? Basically, these electromagnetic radiations are generated by an accelerated charge. For example, we have got a positive charge. This is the electric field. So, a stationary electric charge produces an electric field around it. And where from do we get a magnetic field? This is a wire and it carries current. And this is our magnetic field. So, a wire that is carrying a current, the magnetic field loops around that current. Okay? So, a stationary electric charge produces an electric field, and a conductor and a current carrying wire, it produces a magnetic field. Now, if we accelerate the charge, accelerating means we have got a charge. If we do one thing, if we oscillate it up and down, right? Or we may wiggle it back and forth, what will happen? Obviously, the electric field that is generated by this charge, it will change. So, an accelerated charge changes the electric field around it. And when an electric field is changed, it gives rise to a magnetic field. This electric field, when it changes, it gives rise to a magnetic field. And the reverse also happens. When magnetic field is created, because of the change in electric field, this magnetic field is also changed. So, this magnetic field gives rise to a changing electric field. So, sort of a cycle is set. Electric field, electric field. They go on generating these changing electric fields, generate changing magnetic field, and changing magnetic fields generate changing electric fields. Like this. Electromagnetic radiations are nothing but the changing electric and magnetic fields. These changing electric oscillations, these changing magnetic oscillations, they constitute the electromagnetic radiations. But one thing has to be kept in mind, these two oscillations, the electric field and the magnetic field, these are perpendicular to each other. Like, if this is the electric field, this will be the magnetic field, right? Like, if this is the electric field, this will be the magnetic field. Okay? I hope it's clear. Now, the third thing is in which direction the current will propagate. Electric field perpendicular to magnetic field, and the direction of the current, it is perpendicular to both these, both the electric field as well as the magnetic field. So these three things, electric field, magnetic field, and the direction of propagation of the electromagnetic radiation, they are mutually perpendicular, right? So how do we represent this electromagnetic radiation? We have to remember that this electromagnetic radiation is transverse in nature. First, what's transverse? Transverse is when the particle, it oscillates up and down, and the direction of the current is perpendicular to it. This is the direction of the oscillation, and this is our direction of this electromagnetic radiation, right? This particle oscillates at 90-degree angles to the direction of the current, and this will give us a transverse wave. So this is the direction of current. Let us say this is the electric field. This will be our magnetic field. I have shown two waves through transverse oscillations. First electric represented by E, and then magnetic. These two are perpendicular to each other. This is the electric oscillation. This is the magnetic. These two are perpendicular to each other and they are perpendicular to the direction of the current. So these three are mutually perpendicular. Now, if we just try to understand it on the plane of this board, right? This is the electric field. This is the magnetic field. What will be the direction of the propagation of the current? This is in the two-dimensional plane of the board. The direction of the current, it will be like this. The direction of the radiation, electromagnetic radiation, it will be perpendicular to both electric field as well as the magnetic field. I hope it is clear. Now, let's try and understand the features. What are the features of this electromagnetic radiation? For this, I will simply draw a transverse wave to represent an electromagnetic radiation. Now, this is our crust, this is our trough, this is the amplitude, wavelength, right? This is the central axis, this is the central axis. These oscillations above this axis, they are the crusts, down it they are the troughs. The maximum distance from this central axis to the crust or to the trough is the amplitude. The distance between two consecutive crusts or even these two troughs, this is our wavelength. This or this, either of the two, these are our wavelengths. One important thing that we do come across electromagnetic radiations, that is the frequency of the electromagnetic radiation. What do you understand by the frequency of an electromagnetic radiation? As I have already told you that the oscillations, the particles, they oscillate like this. These are the electric field oscillations or magnetic field oscillations. They pass through the central axis through a point. They pass through a point. The number of oscillations that pass through a point per second. I am repeating, the number of oscillations that pass through a point per second, that is our frequency, right? So greater the frequency, greater number of these cycles pass through a point per second. One cycle is from this point and again when it reaches the same point, this is one cycle, right? Now, other thing is time period. What is time period? For time period, we will again remember this frequency. As frequency says the number of oscillations passing through a point per second, time period is the time taken by one cycle to pass through a point. The time taken by a cycle to pass through a point. It's very clear. If the time taken by a cycle is more, that is the time period is more, lesser number of cycles will pass through a point. And what does that infer? That infers lesser will be the frequency of that electromagnetic radiation, right? And there is a particular relationship between the frequency and energy of radiation. The frequency determines the energy of radiation. And how do we write it? We write it as E is equal to h nu. E is equal to h nu, where E is the energy, h is Planck's constant, and nu is the frequency. This was given by Max Planck. So greater the frequency, we can see H is a constant. So we may even write E is directly proportional to frequency. Higher the frequency, greater is the energy. Again, as I have already told you about wavelength, the distance between these two, there is a relationship between this frequency and wavelength, and that's like mu is equal to C by lambda. C is the velocity of the electromagnetic radiation. As we see this mu, it is inversely proportional to wavelength. That is, if the frequency is high, wavelength is low, and vice versa. I hope it is clear what are electromagnetic radiations, how are they generated, what are their features. Now, I'll be briefly discussing with you electromagnetic spectrum. First, what is an electromagnetic spectrum? These electromagnetic radiations, when they are arranged on the basis of these frequencies or wavelengths, we refer this range as an electromagnetic spectrum. Let me just try and explain it. All the radiations we come across are part of this electromagnetic spectrum. Let us start with something that we encounter daily, or what we are aware of. Let us talk about visible range first. Visible range is a part of this electromagnetic radiation. This is our visible range. Our visible range starts from violet and extends up to red color. And the frequency, it is increasing frequency, so obviously decreasing wavelength. Frequency increases in this direction and the wavelength will increase in the opposite direction. Now this visible range, its frequency starts from approximately, this is 4 into 10 raised to the power 14 hertz to 7.5 into 10 raised to the power 14 hertz. And if we talk in terms of wavelength, it will be something like 750 nanometers to 400 nanometers. These are the approximate values. Now we have got radiations beyond this also. Beyond this range we have got radiations, and before this also we have got radiations. Like we have got X-rays, gamma rays, microwaves, these infrared, ultraviolet. Let me first write down these ranges. It starts with radio. This is micro, infrared, ultraviolet, X-rays and gamma rays. So what it is like? It is radio waves, microwaves, infrared, visible range, ultraviolet, X-rays and gamma rays. Now sometimes you are asked which in our exams also, in the multiple choice questions, which has got the greater energy? Is it micro or is it ultraviolet? And at the time of examinations particularly, it's very difficult to recall. So I have tried and designed a trick for it. My nickname is Ruhi. So how I have just tried to make a trick for it. It is Ruhi, ma'am, is vividly, vividly means clearly. Ruhi, ma'am, is vividly understanding X-rays, gamma rays. So what is it? Ruhi, ma'am, is vividly understanding X-rays, gamma rays. R from Ruhi, that's radio waves. M, ma'am, for microwaves, is infrared, vividly visible, understanding ultraviolet, X-rays and gamma rays, you know. If you remember this sentence, it is not very difficult to remember. If you remember this sentence, you can very well predict which ray has got greater energy, which ray has got greater frequency, because I have clearly said I have arranged it on the basis of increasing frequencies. That means gamma rays have got greater frequency compared to X-rays, ultraviolet, visible. So as you move just ahead in this range, the frequency goes on increasing, the energy goes on increasing, wavelength goes on decreasing, right? So by remembering this simple sentence, you can predict the energies, wavelengths and frequencies for different radiations. I hope I have made it clear. Thank you so much. Thanks for watching and thanks for your patience. Thanks.